Welcome back to our lecture series on the course Material Science and Metallurgy. So today we will discuss a topic on the surface and volume defects in solids. So a couple of classes back we started with crystal defects in solids. We have seen with the classic case study of Titanic. Then we have discussed little in elaboration about point and line defects. In today's class we will see surface and volume defects in solids. So before starting, let us review what we are going to discuss in today's presentation. So we will, in brief, we will recap on the point and line defects in the crystal defects. Then we will talk more about surface defects, which is a two-dimensional defect. So under which we will see what are the grain boundaries, twin boundaries, and stacking faults. Then we will discuss about volume defects. Basically, they are the three-dimensional defects under which we will see voids and cracks, the inclusions, and we will summarize at the end of our lecture. We have quoted this that no solid material is perfectly structured. So that means all the materials is observed with certain level of defects that are present in the material. So defects exist at the atomic level. These defects influences strength, conductivity, and durability mainly. The type of defects what we have discussed so far is the point defects, which basically affects at the individual atom level. So that is a zero-dimensional level. So we have discussed about under which we have discussed vacancies, which are the empty regions or the missing atoms. The presence of missing atoms creates a vacancy. Atomic level, obviously. So interstitial. So in between the spaces that are present between the regular arrangement of atoms, if a foreign atom has been occupying that particular site, that is treated to be an interstitial defect. Then in place of original atom, if it has been substituted with another foreign atom, so that is treated to be a substitutional defect, and we have seen it under the point defects. Then we have also discussed line defects. If a row of atoms having certain misalignment or missing from the regular arrangement, then such defects are treated as a one-dimensional defects, are also called as dislocations, or also considered as line defects, under which we have discussed edge dislocation and screw dislocation, where you will be seeing the spiral movement of the atoms, spiral dislocation, right? So in today's class we will discuss more about surface defects, which are grain boundary misalignment in short, majorly what we will consider, and volume defects, under which we will see cracks, voids, and inclusions. So let us go into this surface defects, the characteristics and their effects. So before that, if we define a surface defect is an imperfection that occurs at or near the surface of a material, disrupting the regular atomic arrangement. So if we closely observe this particular picture that is provided, so let us consider these are the grain regions. Okay, these are the grains, individual grains. So these are the individual grains here, right? This is a one grain and this is another grain. Okay. So this is a one grain and this is another grain, individual grain. So the regions, the common region that you will be seeing, that is treated to be the boundary for both the grains. So that particular, in those regions also atoms will be staying. Those atoms are considered to be the grain boundaries, and that is considered to be a defect region, because there is no regular arrangement that is observed. That will not be having, the atomic arrangement will not be regular. It will not be the crystal A or the grain A arrangement, regular arrangement, not like this. Then crystal crystal 2 or nothing with the grain 2, it will not be having the grain 1 orientation or the grain 2 orientation in this particular grain boundary region. So that's why this is considered to be a two-dimensional defect, and which is called as grain boundary. So in short, surface defects is considered as an imperfection that occurs at or near the surface of the material, which basically disrupts the regular atomic arrangement. So under this we have majorly three types of surface defects. So first one is grain boundaries, what we have discussed just now. It is an interface between different crystal orientations. So you have one crystal here, you have another crystal here, that is a grain A and grain B, and you have orientation. Let us say this is a one region, this is let us consider this is a crystal, and this is so this is a grain 1 and this is grain 2. The region that resides, the atoms that are residing in this particular region, that those atoms will not be having the grain 1 orientation or grain 2 orientation, that's why it is considered to be a defect region, and that which is called as a grain boundary. So that is basically an interface between the two different crystal orientations. Then we have the twin boundaries. Twin boundaries are symmetric mirror image boundaries, basically. So which is having a symmetric shape that can be repeated along a particular plane, over a particular plane, just similar to the mirror image boundaries. We will see in short. Then we have the stacking faults. Stacking faults are caused due to the disruptions in the regular stacking sequence. So if the atoms are been stacking in this way, so next again something like this, again something like this. Instead of that, again another disruption has happened and another orientation is also similar to this. Then we have, this is considered to be a stacking sequence defect. So that is called as faulty stacking. A disruption that is observed in the regular atomic stacking sequence, that is also considered to be a surface level, and it's basically a two-dimensional level, a planar atoms, disruption that is observed in the planar atoms. So if you look at an example, fine-grained metals have more grain boundaries, making them stronger but less ductile due to hindered dislocation moment. The metal which is having fine grains will be having more grain boundaries. That means grains are very, very small in size, fine-grained metals. So as the grains are very small, the grain boundary regions, the interfaces will become more. When you have the more boundaries are there, so dislocation, when a deformation is occurred on the metal, these dislocations will be moving and arresting at the grain boundaries, and that causes the material to be, that strengthens the material because of the fine grain structure, but it will be having less ductility, right? In short, that is one of the strengthening mechanisms which we will see in our next class. So let us discuss more about grain boundaries here. So grain boundaries, as I mentioned, it is a region where two or more crystal grains meet. So this is the one region and this is another region, that is one. All these are basically grain boundary regions. These are all the grain boundary regions. All these are grain boundary regions. It is a region where two or more crystal grains meet. So what are the effects? If more grain boundaries are there, what are the effects? Basically, it increases strength. More boundaries blocks the dislocation moment. Let us consider an external load is being applied on the metal. So what happens? Because of that external load, the atoms will try to move. So wherever the dislocations are there, these dislocations starts moving. The dislocation moment will be progressed and it will reach to the boundary region. At that particular boundary region, because of the irregular atomic arrangement, these dislocation moment will be arrested at that particular region. So grain boundaries, if more grain boundaries are present in the material, in short, it will be increasing the strength of the material. So always we seek for fine-grained structure in the metals to have better strength for the material. Then it reduces the conductivity because there is no regular arrangement. Irregular atomic arrangement causes the conductivity or the electron, it hinders the electron flow, it obstructs the electron flow. So it eventually reduces the conductivity. It has positives as well as the negatives as well. So it enhances corrosion, more reactive region, because it is having irregular pattern. So atoms are exposed to the surface and they freely can react with the external materials or the gases. So it will be forms into a new oxide layer, or it could be another compounds can be formed. So due to that, reactive substances can be observed in the metal. So that in short, I would say that. So it promotes corrosion, oxidation, promotes corrosion for the metals, especially iron, especially. So if I consider one example, so small grain sizes in metals like steel increases the hardness, because small grains will enhances the dislocation moment, and in short it will be increasing the certain strength and certain mechanical properties. That also includes the hardness. Hardness is also can be improved by considering the fine grains. Then we have the twin boundaries and stacking faults. First, let us discuss about twin boundaries. As I mentioned, twin boundary is a mirror-like symmetry that is observed in the lattice structure. If we closely look at the image, so we have the grain boundary here. These are the grain boundaries. This is a grain 1 and this is a grain 2, and this region is the black highlighted region, that is a grain boundary in this particular case. So this is a grain 1 and this is a grain 2. So we have this black highlighted region, that is basically the region. This is considered to be the grain boundary region. If we present it in terms of the atoms, you have the regular atomic arrangement of atoms which is having this particular inclination. Regular atomic arrangement, you can see the grain 1 is having this particular inclination, and atoms are aligned to that particular inclination. All atoms follows the regular arrangement. Similarly in the grain 2 also you can observe which is having in this direction you have the inclination, and along this particular direction all the atoms are being aligned. So in this particular region where the dotted vertical line indicates a grain boundary region. So in this grain boundary region there will be no regular arrangement. It will not follow either the grain 1 or grain 2 regular arrangement of atoms. So if we look at what is the twinning, so what happens is we have the two grains, and you will be seeing, instead of having a irregular arrangement in the grain boundary region, the atoms will be arranged to a particular direction. So it is something like a folding. So two grains are being folded to one over the other. So when you apply with the shear loading into the material, so sometimes these atoms overlap. During this overlap, so it aligned to a particular direction which is not related to any of the grains. So in this particular regions is called as a twinning. So these are the twinning region, and in this particular direction you will be having a mirror-like symmetry here. Along this particular direction, in this particular direction, the TB plane, the matrix has been here, just a mirror-like symmetry can be observed. So if a mirror is present, so just in a opposite way, so it will be observed. The same structure can be observed. So that kind of defect region is considered to be the twin boundaries. That particular region, the plane, the atoms associated with that particular plane is considered as a twin boundary region. So what it does, it enhances the ductility in some of the metals, not in all metals, but in some of the metals it enhances its ductility. Previously we have seen the grain boundary reduces the ductility and increases the strength, but here the twin boundaries increases the ductility in some of the metals. Mostly these are found in materials like titanium and stainless steel. So SS and titanium materials, these twin boundary defects can be observed. Then we have discussed about the stacking faults, which are irregularities that are observed in the atomic stacking sequence. So which can impact basically the plastic deformation in the materials, in the metals especially, particularly aluminum. So it impacts the plastic deformation in the material because of the stacking plane, entire plane of atoms which are considered as a irregular. Instead of having a regular sequence of stacking, you have one plane which is having a disturbed plane of atoms, so irregular stacking sequence. So that causes that impacts the plastic deformation, particularly in the aluminum. Then we have volume defects. Volume defects are considered to be the structural weakness for the material if they are observed. So how do we define it? So a volume defect is a three-dimensional imperfection. It's a three-dimensional imperfection that is observed within the bulk of materials that disrupts its uniform structure. So at the bulk scale, at the bulk level, at the three-dimensional material level, it disrupts the uniform structure in its presence. It's basically a three-dimensional imperfection that is observed. So we have under this volume defects, majorly we have voids and cracks and inclusions. Voids, what are the voids? Empty spaces that are present due to the missing atoms at the three-dimensional scale level. So you will be missing not a single atom, you will be missing more or group of atoms or more number of atoms. It creates certain voids, certain empty region. So that empty region or vacant region, that is considered as a void, and which is a volume defect here. We have the cracks, that's the structural breaks that are observed in the material. So it could be a fine crack or it could be a hairline thin cracks, and it depends, but it will be impacting majorly the strength of the material. So which are also considered to be, these are voids and cracks also considered to be the fracture initiation points they're observed. And we have another type, that is inclusions. Inclusions are the foreign particles that are trapped in the material, foreign particles which are trapped in the material during the manufacturing, that is considered to be the inclusions, material inclusion. If we recall our classic case study of Titanic, so we have discussed that rivets are being observed with high slag content, which is forming the weak inclusions that cause the fracture. In our NIST website, official website of United States, they also mentioned how tiny rivets that are present. The article title of how tiny rivets doomed the Titanic vessel. They have given this analysis as well, the stress analysis. Where are the regions, stress concentrations regions, because of this thin riveted joints that caused failure of the entire ship when it has been impacted with an iceberg. And fractures in the hull plates led to the rapid entry. Both are considered to be the volume defects. One is causing due to the inclusions, the presence of foreign particles in the material, the slag contents, that is high slag content that is observed in the rivets that cause the weakness in the material, as well as the impact caused the fractures in the hull plates, which led to the failure and the rapid entry into the vessel. So in short, voids, as we have discussed, certain image is also given, microscopic image, which is a diameter of 5 to 8 mm void that is observed, that is a photograph, microscopic image, that is formed during the forging of large cast ingots. So in this article, they have presented this microscopic image, which has been noted with 5 to 8 mm of void and the empty space. These are the empty regions formed during the manufacturing process, especially during the casting. Also, we observe it most often. There will be some certain trapped gases. Gases will be trapped in the material, and that causes this voids. Empty regions formed by the trapped gases and or the missing atoms. Obviously, when there is no material, the material strength and overall integrity of the material will be dramatically reduced. For example, if we consider the voids example in this particular case, the porosity can be observed in most of the casting, which reduces the structural integrity. Then we have the cracks, the hairline cracks. Most of the cases, in general scenario also, we see the cracks. Cracks are the stress concentration regions, which eventually leads to the catastrophic failure. And cracks are the points where the fracture initiates and it progresses, and eventually it creates a catastrophic failure of the material, or in short, the unit or the item. Then we have it initiates a fracture mechanism, which basically cracks are the one which introduced the study about these cracks, which initiated the fracture mechanical, the whole subject, the fracture mechanical analysis in the engineering domain. The study about the cracks and the fracture behavior, fracture initiation, and the progress on the load application, and that basically initiated this entire subject, the ocean of fracture mechanics analysis in engineering. Most of the design engineers before manufacturing a product now, they were doing this analysis, fracture analysis, and observing the crack and failure and at what point, and the strength and safety of the material has been ensured with this analysis. Now coming to the inclusions, as I mentioned, it is foreign particles that are present inside the material. These foreign particles could be the oxides or the carbides. When a material is exposed, certainly in the case of iron, when it is exposed to the salt water or the humid environment, it reacts with the oxygen that is present in the atmosphere, and it forms into iron oxide, which is, we are calling it as a corrosion or the oxidized form of iron. So these oxides are considered to be the foreign particles that are incorporated in the material, and that is basically, since it is a foreign particle, so it is considered to be a defect region or the imperfection. So these are the foreign particles inside the material. What could be the impact of these inclusions, the presence of inclusions? Obviously, as we have discussed in the Titanic case also, it reduces the strength, the overall strength. Sometimes these inclusions can be intentional to improve the properties, and in some certain scenarios it is undesirable in the case of Titanic, just like, which causes a failure. When it is beneficial, if I give you the example, the presence of controlled carbides, the presence of carbon within the steel, sometimes it will improve the properties, especially the hardness of the material. Then sometimes it is detrimental, which is detrimental, where you will be observing the non-metallic inclusions, especially oxides inclusion, that reduces the overall toughness of the material and weakens strength. For example, in the high strength steels, if we consider, we use the carbide inclusions basically to enhance the wear resistance. In turn, it increases the hardness, and so it will be, in turn, that increases the wear resistance. Carbides will increase the hardness of the material since the formation of the iron carbide. Right. So as we have, if you recall how engineers need to work on these defects quickly. So one need to use it in terms of the heat treatment and reduces this. We have to understand about the heat treatment process and control these defects, reduces this unwanted defects, and by allowing it, we can carefully consider defects for improving the strength, similar to what we have discussed just now, the carbide inclusion in the steel. Then welding and manufacturing, where in the place of riveted joints, that is being considered to prevent the weak joints. In the semiconductor industry, again, the controlled defects that are being added into the silicon, that improves the overall device performance. This is how engineers have been using the defects for improving the materials. So understanding the defects lets engineers design stronger, safer, and more efficient metal, one can say that. So as a part of our lecture, so if we summarize what we have discussed in today's class, we have discussed about surface defects, that includes the grain boundaries, twin boundaries, and stacking faults. Grain boundaries are the interface regions between the two crystals. Twin boundaries like mirror-like defects, mirror-like image imperfections that have been created. Then faulty stacking sequence. These are considered to be the surface level defects. And volume defects, we have discussed voids, cracks, and inclusions with some examples as well. So one can say that defects play a vital role in material properties in engineering applications. So I am once again quoting that defects are not always bad. So understanding about defects is very important, and carefully controlling about this is very much needed for an engineer. So that is very much crucial in material engineering for advancing the materials. So in our next class, we will see we will discuss more about strengthening mechanisms in the material. So utilizing these defect regions, so how you can strengthen further. So especially with the grain boundary concepts, we will discuss how they are helpful in promoting certain properties, improving certain properties. So in our next class, we will discuss more about strengthening mechanisms in the solid. So for making this PPT, I have gone through certain references I have listed out here. And thank you for watching the video.